Today once again I welcome you all in the next session of Dr. Pranav Shrivastav, Professor, Department of Chemistry, Gujarat University, Ahmedabad. Dr. Shrivastav obtained his MPhil and PhD degree in chemistry from Gujarat University in 1993. He has 27 years of teaching and research experience and completed 3 projects from SERV, DST and BRNS. His research interest includes bioanalytical investigation of drugs and their metabolites in early drug development phases using ultra-performance liquid chromatography, tandem mass spectroscopy and supercritical fluid chromatography with special emphasis on stability and matrix effect for quantitative bioanalysis. Dr. Shrivastav has delivered more than 55 invited talks at various seminars, workshops, conferences in India and one in the US. He has authored 236 research publications in national and international peer-reviewed journals, guided 25 PhDs and 13 MPhil students. Also, he is an editorial board member of Journal of Pharmaceutical Analysis, Elsevier Sciences, Biomedical Spectroscopy and Imaging, iOS Press, American Journal of Modern Chromatography, Columbia International Publishing, and Journal of Chemistry, Hindway Publishing. Dr. Shrivastav has reviewed more than 500 research articles and review articles of different journals from American Chemical Society, Elsevier Sciences, Royal Society of Chemistry, Ville Interscience, Springer, Taylor and Francis, and many others. In addition, he has co-authored a chapter on current understanding of bioanalytical assay reproducibility, incurred sample reanalysis, incurred sample stability, and incurred sample accuracy for a handbook of LCMS bioanalysis best practices, experimental protocols and regulations, John Ville and Sons, and a chapter on UHPLC and sub-2 micrometer particles for a book entitled Chromatographic Stationary Phases, Recent Advances and Novel Applications, Future Sciences UK. Apart from this, he has written editorials and commentaries for a prestigious journal, Bioanalysis, Future Science UK. Thank you.
Hello everyone. I am Prof. Shrivastav from Department of Chemistry, Gujarat University. First of all, I'd like to thank UGC Human Resource Development Center of Gujarat University for giving me this opportunity to be a part of this second online refresher course in chemistry and speak on a topic of current interest, that is green analytical chemistry, a step towards sustainable method development. I take this opportunity to thank Dr. Jagdish Joshi sir, Professor and Director of UGC HRDC, and the course coordinator Dr. Dilip Vasawa sir from Department of Chemistry, Gujarat University, and all the associated team members. I congratulate you for your sustained efforts after a hugely successful first online refresher course in chemistry last year. HRDC Gujarat University is ranked 15th in India and is first in the state of Gujarat. HRDC GU was the first in organizing online refresher courses in India in the year 2018-19, which had about 2,500 participants. Apart from this, there are several other activities in which HRDC of Gujarat University has done some remarkable work. They have developed e-content for several online short-term courses, out of which around 5,000 participants have successfully completed 130 online courses. Further, an online short-term course was organized for administrative staff of universities during lockdown, which had a participation of about 105 participants. Apart from this, they have initiated several blended courses, especially for PhD scholars, and more than 900 scholars have benefited out of these courses. The contents of my talk today includes a brief about analytical chemistry, some recent trends in analytical sciences, green approach in analytical chemistry or analytical sciences, then a comparison between what is green chemistry and what is green analytical chemistry, followed by different approaches for green analytical chemistry metrics, how can we calculate method greenness, and then I'll be explaining one of a very important greenness metric tool, that is AGREE, analytical greenness, how it can be calculated for any analytical method. And finally, there will be few applications, case studies where this AGREE matrix has been applied to find out method greenness. The learning objectives for this presentation includes, first of all, understanding what is green analytical chemistry, how it is useful in sustainable development, knowing different metric tools to evaluate method greenness, and of course calculating the method greenness using AGREE metric tool, which is one of the most currently used tool to measure method greenness. Before I go on to green analytical chemistry, a brief overview on analytical chemistry, which deals with material characterization. It is basically a method science, and it helps to provide qualitative information or quantitative information about a material or a sample in any form. It can be a solid, liquid, or a gas. Analytical chemistry plays an enormous role in our society, such as in drug manufacturing, process control, medical diagnostics, food production, forensic surveys, and many such others. It is a science that is directed towards creating new knowledge so that chemical analysis can be improved to respond to increasing or new demands as far as analytical science is concerned. The last couple of decades have been very eventful in the area of analytical instrumentation, especially in terms of technological changes. Increased application of nanotechnology, automation, and artificial intelligence has led to a totally new generation of smart technologies that are much more compact, faster, and also accurate. The major focus has been on miniaturization, as instruments consume considerable amount of energy. Apart from this, the other focus is on automation and hyphenation or integration of different equipments. In hyphenation, two or more techniques or tools are combined to solve many complex analytical problems. For example, one can combine a chromatograph with a spectrophotometer or a spectrometer, like for example HPLC, and combining it with a mass spectrometry. All of this miniaturization, automation, hyphenation, they contribute towards principles of green approach in chemistry or analytical chemistry. The whole idea of green chemistry has its roots in sustainable development. The initial attempts for sustainability were directed towards industrial scale processes and products, as proposed in the principles of green chemistry by the pioneers Anastas and Warner. Green analytical chemistry has emerged from green chemistry in the year 2000. It emphasizes on the role of analytical chemists to make laboratory practices more environmentally friendly. Apart from the development in instrumentation and analytical methodologies, which are essential for improvement in the chemical analysis, efforts are generally being made to reduce the negative impact of chemical analysis on the environment and also to enable implementation of sustainable development. Principles having all this basically is intended to have a green approach in analytical science without compromising anything in a chemical lab. Having said that, there has to be a good balance between increasing the quality of results with no compromise in the performance and improving at the same time improving the environmental friendliness of analytical methods. Green analytical procedures are those that are more environmentally benign and are safer to humans. The greenness of analytical methodologies is basically a multivariate and a complex parameter that cannot be easily quantified. That means one needs to assess many parameters in analytical science to award greenness to any analytical methodology. The green chemistry metric systems are mainly applied in chemical synthesis. This is what we are aware of and is usually referred to the mass of the product formed. Whenever we do any chemical reaction, we obtain a product, and that is where we apply rather green chemistry principles as far as organic chemistry is concerned. But unfortunately, there is no product formed in analytical chemistry, and hence there is no change in the mass. So one needs to look at some different aspects in analytical chemistry to make it a green analytical chemistry. Now, if you look at the 12 principles of which were proposed by Anastas and Warner in 1998, what we find is that out of those 12 principles, only 4 principles can be directly taken up in analytical chemistry. The first one is prevention of waste, use of safer solvents and auxiliaries and other compounds, design for energy efficiency. Now, this is a very important aspect in analytical science. Reduction of derivatizations. As much as possible, there should be no derivatization in any process. That is what is being propagated in green chemistry principles. Now, this is a comparison between green chemistry principles and the corresponding green analytical chemistry principles. And this is signified in green analytical chemistry by a mnemonic, that is significance. I have highlighted with same color on both the sides for those principles which are common in general chemistry principles and in green analytical chemistry principles. The mnemonic, as I said, is the significance. Select, integrate, generate, never, implement, favor, increase, carry, avoid, note, choose and eliminate. These are the words which have been selected to give a mnemonic to this green analytical chemistry principles. The key considerations of green chemistry, which forms the backbone of green analytical chemistry, includes elimination or reduction of use of chemical substances such as solvents, reagents, preservatives, additives for pH adjustments, and many others. The second is use of environmental friendly sample preparation techniques such as ultrasound. Now in ultrasound, it uses high frequency acoustic waves to create microscopic bubbles in liquids. And with the collapse of the small bubbles, shock waves are generated. And they help in breaking up or promoting dissolution of solids. Apart from ultrasound, there is microwave assisted extraction, supercritical fluid extraction, use of supercritical substances, superheated water extraction, use of special membranes, cloud point extraction, which generally is devoid of organic solvents. Apart from these two, the other component is that of proper management of analytical waste. This has also become very important. How do we manage the waste which is generated? Minimization of energy requirements. That is, as I said, it's a very key component in green analytical chemistry. How well we can minimize use of energy. And at the same time, prime consideration is given to the safety of the analyst or the operator. Now, this has also become important so that the analyst is less exposed to the entire system. That means hermetization of analytical systems is also warranted. Currently, there are different approaches in green analytical chemistry to calculate method greenness, and this is given by some metric tools. I have mentioned here 6 GAC metrics which help us in evaluating or assessing the analytical method towards method greenness. Each of them have their own advantages and limitations and are based on the canons of green chemistry principles. National Environmental Method Index, that is NAMI, Analytical Eco-Scale, this is also a very promising tool. Multi-Decision Criteria Decision Analysis, MCDA. GAPI, that is Green Analytical Procedures Index. The 5th one is Red, Green, Blue, RGB Additive Color Model. And the 6th one, which I will be dealing with in detail, that is AGREE, Analytical Greenness Metric Tool. We'll be considering each one of these metrics one by one, but my major emphasis would be on the 6th one, that is AGREE metric tool. Now, National Environmental Methods Index. This is one of the oldest tools used to assess the greenness of analytical procedures. This metric system is based on a simple pictogram, as one can see here, a circle with 4 quadrants. Each part reflects a different criterion, such as PBT on the left hand side, persistent, bioaccumulative and toxic chemicals. On the right hand side we can see hazardous chemicals used in the procedures. Now the chemicals which are considered to be hazardous are listed in the Resource Conservation and Recovery Act as D, F, P and U hazardous list. So there is a big list of chemicals which fall under this category of hazardous substances or chemicals. Plus we can see another parameter, that is waste. During the procedure, less than 50 grams of waste is produced. That is what is intended in any process. And the fourth one is corrosiveness. This is another factor which contributes towards method greenness, and it signifies that our method should be compatible within a pH range of 2 to 12. And if you can see this pictogram in the center, if a method is characterized as not green, then that quadrant is left unfilled. That means it is totally white. And if the method is green, then that quadrant is made in green color, or a green color is given to that quadrant. If you look at this pictogram, what we find is that the method is green with respect to PBT and corrosiveness, but it involves hazardous substances and it generates more than 50 grams of waste for a particular analysis. This metric system has some limitations. First of all, it is time consuming, as one needs to look into the list of Environmental Protection Agency, the list of chemicals that are harmful or toxic. Secondly, it does not consider the criterion of energy consumption, which is a very important aspect in green analytical chemistry. So it does not cater to that. At the same time, it gives us a qualitative assessment only. It does not give us a quantitative assessment. We want a quantitative assessment. That means how much quantity would contribute towards greenness and how much of it would not contribute towards greenness. The second one is the analytical eco scale, which is based on awarding penalty points if something is not green. So it is more quantitative rather than qualitative when we compare it with the previous one. Analytical eco scale is a novel, comprehensive approach which is based on penalty points to parameters of an analytical process. As one can see here, there are different penalty points which are given to the reagents. At the same time, the amount of reagent or the volume of reagent which is used is also considered in awarding penalty points. Hazardness level is also being given some penalty points. At the same time, energy, occupational hazard, as I was telling you, hermetization of analytical process. Hermetization means a person, an operator who operates that instrument is less exposed to the entire process. That means if you have a totally automated kind of a system, the person who is working on that instrument is less exposed to any kind of possible hazards. It will not affect his or her health. That is also being given an additional weightage in greenness, because it may happen that in a very sophisticated process there would be some emissions of some vapors, and the analyst might be exposed to such vapors. Also, due consideration is given to waste generated, the amount or the volume of waste generated, and whether the waste generated can be recycled or how it can be treated, number of steps involved in treating the waste also contributes towards method greenness. However, there are few limitations to this approach. No information is given about the structure of the hazards which are being considered here. Lack of information on the causes of environmental impact of the analytical procedures, such as the use of solvents, other reagents, or other occupational hazards, any quantitative measures, and no information about the possible threats or the number of threats which an analyst is exposed to. The third metric, that is multi-criteria decision analysis, MCDA. This analysis is mainly used in environmental sciences and environmental management. Basically, it deals with social, environmental, economical, and technological criteria during decision making. That is why it has the name decision analysis. Now, this is a criteria which has a bearing on the experience which an analyst carries in executing a particular process in analytical chemistry. Here, weightage is given through expert opinion or experience in choosing an appropriate procedure. Selection of criteria is based on metrological, economical, and environmental criteria, and it applies a procedure called Prometheus, which is a metric tool which is referred to as preference ranking organization method for enrichment evaluations. Now, this is a criteria or a metrics which gives us some information about how much the method is green, but there is a limitation as attached to it, that is, again, it doesn't give you via a quantitative information. There is no information about the energy consumption. It does not talk about the process of derivatization, which is one of the criteria in green chemistry. It gives us qualitative information. And in terms of greenness, it is considered as a mild green method or a metric tool. It doesn't give us a complete greenness as far as the criteria is concerned. The fourth one, that is Green Analytical Procedures Index, that is GAPI, is a process which is symbolized with 5 pentagons, and these pentagons are used to evaluate and quantify the environmental impact involved in each step of an analytical methodology. This is a very important aspect here, that this is one tool which considers right from sample collection to final determination. As we can see here, the pentagons refer to different aspects of analytical methodology. Sample preparation on the left hand side. Then we have reagents and compounds that are being used. Instrumentation. What kind of instrumentation is being used? Because, as I told you, instruments consume considerable amount of energy. How the sample was collected, how it was preserved, how it was transported to the lab, etc. Everything is being given due consideration. And if you can see the pentagon in the center, which has a circle, that circle signifies whether it is a quantitative method, and if there is no circle in that pentagon, it signifies it is a qualitative method. Here if we see, these are a few examples, simple examples to understand what it shows about method greenness. Here, three principal colors, namely green, yellow, and red, depict low, medium, and high impact. That means green gives us an indication that it is low impact in as far as environment is concerned. Yellow means medium impact, and red means a very high impact. Now, if you can see in the first example, the top, the penalty points awarded to a particular method represented through these 5 pentagons is 52. And therefore, if we subtract this from 100, the method now has a score of 48, which is not considered to be a good method as far as greenness is concerned. If you look at the next one, just below that, what we find is the penalty points are 43. That means as the penalty points go down, and one can see very well how that red color is gradually being replaced by either green or yellow. That means the environmental impact is less, and therefore the score now becomes 57. And likewise, if you see on the left hand side, the penalty points are 15 only. That means the score is very high. This is a very good score, that is 85. And we can see more of green color naturally. And these pentagons, as I said, as I mentioned in the previous slide, signify different aspects or different steps of any chemical analysis. Though it has several advantages, but still the only problem here is that it does not consider all 12 principles of green chemistry. That is what is the missing thing in this metric tool. The fifth one, that is red, green, blue, RGB, additive color model. This is also a comparative model. If we compare it with the previous one, it gives us a very good comparison between this model and the previous one. But it has a different way of expressing method greenness. It uses 3 primary colors which act as 3 main attributes. If you look at this figure, what we find is the red signifies analytical performance. See, we want good analytical performance for any method. Green gives information about safety and eco-friendliness, and blue signifies productivity or practical effectiveness. All these 3, they contribute towards how best we can award greenness to our method. In between, if you can see, you find yellow color, magenta, and cyan. And then in the center it is written white, which is considered to be an ideal color. Now, how this is being defined, all these colors define to what extent the method is green. Now, this is evident from the next slide. Now, what we can see here is red, green, and blue color score on the left hand side, the final color of the method in the center, and the general implications, the output, on the right hand side. What we find here on the left hand side is if all 3 colors contribute greater than 66% satisfaction, then that method, the final color of that method is white, and that means that method is a good choice, and it will give us a very good greenness. Then comes magenta. What we find is that the red color, that is the performance, and the blue color, that is the productivity, is greater than 66%. But if you look at the safety or the eco-friendliness, that lies between 66 and 33%. That is the range. So that means there is slight decrease in the safety of that method, and therefore it is awarded a magenta color. And likewise, if you go on to see yellow, cyan, they are all based on the two things, that is degree of satisfaction and degree of tolerance. If the satisfaction is greater than 66%, better is the greenness of that method. And if we go down, what we find is all three have less than 33% of satisfaction, and therefore a black color is awarded to them, and therefore that method may not be a good method as far as awarding greenness is concerned. So this method basically is awarding different types of colors to show whether a method is green. It doesn't signify green color as the greenness, but through different colors we come to know how our method is green. Now this is the sixth metric, and this is where I would be focusing more in my talk today. This is one metric tool which caters to all 12 principles of green chemistry, which was not possible with the previous 5 metric tools. And this metric system has been characterized through comprehensiveness of input, flexibility of input, simplicity of output, and clarity of output, which includes, that means it gives us a complete information, qualitative and quantitative information for all 12 principles of green chemistry as applied to green analytical chemistry. And it includes material requirement, that means it takes into account quality, quantity, and toxicity of the reagents or solvents or chemicals used, number of procedural steps which are being used in a process. Less number of steps, better is the greenness. Energy requirement, generation of waste, safety of analyst, miniaturization, this is important aspect, and automation. So it considers all 12 principles of green chemistry. In this metric tool, the input criteria refers to the 12 significance, that is the mnemonic principles, and can be assigned different weights that allow for a certain degree of flexibility. And each of the 12 input variables is transformed into a common scale of 0 to 1. Now this is a very important aspect. For each and every principle which is relevant to the green analytical chemistry, that greenness is transformed into a unified scale of 0 to 1. As you can see in this representative pictogram, all 12 principles are being awarded some colors. Red, then orange, and then yellow, and then light green, and then dark green. This is how this scale is made up of. As you can see on the vertical scale on the extreme right hand side, red shows that it is a 0, and total green gives us a value of 1. The performance of the procedure in each principle is reflected with the intuitive red, yellow, green color, while the weight of each principle is reflected with the width of the corresponding segment. Now, the width, if you can see the width of each segment, some are very small, some are very big, which signifies the weightage of that particular principle in awarding greenness to a particular method. Now, this is a very simple and easy to use, user-friendly tool, and one can easily download it. I have mentioned the site from where one can download this, and one can easily put in the values, and one can get a score for each and every principle. And if you can see in the center, there is a value called 0.68. That is the overall greenness of the method. 1 means totally green. So it is somewhere in between, like 0.68. The higher the value, better is the greenness of that method. I've mentioned this slide again just to remind you that these 12 principles are being considered in calculating greenness of a method using agreemetrics. That is the only reason why I've included this slide again here, to make you understand that these principles, all 12 principles, are being used here in agreemetrics, which is not the case with the other metric tools. Now we'll just go by one through each of these principles. Under the first principle, direct analytical technique should be applied to avoid sample treatment. That means as much as possible, one should use the sample as it is, avoiding or having minimum sample treatment. That means you don't consume a lot of energy, a lot of time, resources in sample treatment. Now, if you can see this, the table here, remote sensing without sample damage is given a value of 1. And if you go down and see the last one, external sample pre-treatment and batch analysis, that means large number of steps, 0 is the score for that. So we need to work with samples with which, or rather which require very less number of sample preparation steps, because sample preparation step is an integral part of any chemical analysis. It is not always possible, that samples can be directly taken up for analysis. But at the same time, if one can minimize the number of these steps, one can award better greenness score to one's method. The goal of the second principle is to have a minimal sample size and a minimal number of samples. Now, this is also very important, that minimal sample size and minimal number of samples, which means that if you work with very small amounts, say for example, in the range of 10 to 100 milligrams or microliters, a score of 1 is awarded. And if you work with macro amounts or in macro analysis greater than 100 milligrams of sample, then one needs to use this equation to find out what is the exact score to be awarded to that principle. Minimal number of samples. Now, if one can achieve the desired output or result with minimum number of samples, naturally you are consuming less amount of time for analysis, less resources, and hence less amount of energy goes into analysis. So these are the two things which form a part of the second principle, that is minimal sample size and minimum number of samples which can be used in our method. Principle third, in situ measurements, direct measurement. This principle aims at the determination of target analytes as directly as possible. The importance is to locate the device close to the measurement location. Now this is very important. If you can do the entire exercise at one place in line, we get a maximum score of 1. If it is online, it is somewhere around 0.66. At line, 0.33. And then if it is totally offline, then we don't get any points for method greenness. The benefits of in situ measurement includes performing chemical analysis with little or no sample treatment, increased safety for the analyst, and minimum use of reagents. That is what is intended in the third principle, in situ measurements. And this is what one can see on the left hand side in the figure, that inline analysis gives us a score of 1. The fourth principle, integration of analytical processes and operations. This is basically intended to save energy and reduce the use of reagents. Decreasing the number of analytical steps as much as possible will lead to savings in materials and energy as well as time. So integration of operations, say for example, if someone wants to do derivatization, then can that derivatization be done online, and then the derivatized product can be directly passed to the measurement device? It is not done offline, it is done online. So basically what one tries to do is to minimize the number of steps which are being used in analytical process, and thereby saving energy, time. Both automation and miniaturization of analytical methods greatly benefit in the use of reagents, solvents, and of course energy. That means if a method is more automatic or automated, and it is miniaturized, because miniaturized instruments require less energy as compared to the conventional sized instruments which are available in our labs. And at the same time, if you go for manual analysis and if the instrument is not miniaturized, then we don't get any score, rather we get 0 as the score. Automation basically of analytical procedures result in lower occupational exposure, especially towards vapors of solvents, and also minimizes risk of accidents. Derivatization, as I was talking about earlier, derivatization should be avoided. In analytical chemistry, derivatization is commonly used as micro extractions to remove any unwanted substances, and that helps in detection of target analytes. Sometimes it so happens that a particular analyte cannot be analyzed by an instrument, so one needs to make a derivative of that. So if that can be done online, or if one can use an instrument which doesn't require derivatization, it will be better. That means if there is no derivatization, a score of 1 is awarded. And if the number of derivatizing agents increases, naturally the scores come down. The assessment criteria refers to the safety of application, environmental fate, environmental persistence, and biological effects. This is mainly because of level of hazards depends upon the nature of derivatization agent. Now this is what is evident in this figure. Derivatization which I use within GC, LC, and chiral analysis. And if there is, as I said, if there is no derivatization, a score of 1 is awarded. And then if we have multiple derivatizing agents, then one has to use this simple equation to find out the final score. The seventh principle, this pertains to analytical waste generated. Large volume of waste should be avoided, and there should be proper management of the analytical waste. Now, this is very important aspect, and again it is a very simple equation to that. If the amount of waste is less than 0.1 gram, a score of 1 is given. That is what we intend to do in our analysis. If it is 10 grams, it is 0.4. For 25, it is 0.25. And if it is 100 grams, it is 0.1. If it is more than 100, then there is no score awarded to that particular method. Or one can use this equation. One can use this equation to find out the score, but that score would be very, very less. So this gives us a quantitative measure as well when we work with agrimetrics. Now the waste generated here is related to liquid or solid reagents, acids, bases which are used, consumables, single-use devices such as sorbents, cartridges, pasture pipettes, filters, etc. In this principle, multi-analyte or multi-parallel methods are preferred over methods using one analyte at a particular time. What it emphasizes here is that if we analyze more number of analytes in a given method, better would be the greenness score. If we analyze, because the principle as it is mentioned is based on the number of consecutive analytes determined in 1 hour. So if our method analyzes only one sample in 5 minutes, that means we can analyze only 12 samples in 1 hour. But if our method analyzes 5 samples in 5 minutes, then we are analyzing 60 samples in 1 hour. So more number of analytes that are analyzed in 1 hour helps us in getting more or higher score. For 70 analytes in an hour, the score is 1. And if there is only 1 analyte per hour, then there is no score at all. And for any other number in between, one can use this equation. Now this ninth principle emphasizes on minimum use of energy for any analysis. The scores are assigned based on energy consumption per analysis for sample preparation, analytical separation, and detection systems. So it takes into account all 3 important aspects of analytical process: sample preparation, analytical separation, and detection. And the energy that is consumed, if it is less than 0.1 kilowatt per hour, then the score is 1 is awarded per sample. And likewise, if the energy goes on increasing, the scores go down considerably. Now the 10th principle, the use of chemicals derived from renewable sources is a promising and desirable approach not only in analytical chemistry but in all branches of chemistry. The scores are based on a straightforward approach. If all reagents are bio-based or no reagents are used at all in a particular method, score of 1 is awarded. And if some of them are bio-based and others are not, then a score of 0.5 is awarded. And if none of the reagents have origin from or a bio source, then a 0 score is awarded. Now in this metric tool, one can feed in the number of such reagents which are used, which are bio-based or which are non-bio-based. And for each of those, one can have a particular score. But this is what it is given only for 1, 0.5 and 0. But one can always add up this in that tool to get the exact score. Now, the 11th GAC principle aims at removal or replacement of toxic reagents by greener alternatives wherever possible. It is not possible to eliminate all the reagents that are currently being used in an analytical process, but wherever possible, if one can use, then one can have a better greenness score. Additionally, the amount of toxic reagents or solvents used is also considered during evaluation. Not that only the toxic reagents used or not, but the amount of those toxic reagents that are being used is also given due weightage. For procedures that consume no toxic reagents, the score is 1, while for others, the mass or volume of reagent is transformed into the score using this equation. And toxicity is defined as toxic towards inhalation, ingestion, dermal contact, or toxicity to aquatic life. The last principle, safety of the operator and environmental hazards. Now this is a very interesting principle and how it is being used. Threats that are not avoidable are counted, and the number of threats are being used to avoid a particular score. Now, what are the threats? These are the 7 threats which have been mentioned. Toxic to aquatic life, that means the chemicals which we use, are they toxic to aquatic life? Are they bioaccumulative? Are they persistent? They are inflammable, oxidizable, are they explosive, or are they corrosive? So the number of such things which applies to a particular reagent, so that many threats can be added in that software. That means the number of threats can be added in that software to get a corresponding score for that. And if there are no threats, such threats, 7 threats which have been mentioned, a score of 1 is awarded to that method. Now, in the last part of my talk, there are few case studies which I would be highlighting, and for which the greenness score was evaluated. Now, this is an example where supercritical fluid chromatography (SFC) was used to separate some antidiabetic drugs like metformin, dapagliflozin, empagliflozin, and canagliflozin. These are all antidiabetic drugs. Now, these are basically achiral in nature. These 4 drugs are achiral in nature. Now, they were separated using SFC on a chiral stationary phase, and that was chiral packed Ig column, which is basically a polysaccharide stationary phase, amylase based, which is immobilized on silica gel. And what is interesting here is that all 4, which are having different physicochemical properties, can be separated using a single mobile phase, which comprises of carbon dioxide, compressed carbon dioxide, along with methanol and isopropanol. And all 4 drugs could be easily resolved. Now, this is not possible with conventional liquid chromatography, and even if it is possible, then there is large amount of toxic organic waste which is being generated when we analyze such drugs all together. Now, to support the experimental results, molecular docking study was performed using a computational tool to get some insight into the mode of interaction of these analytes with the chiral stationary phase, that is chiral packed Ig column, and also to know whether this elution order is observed and why it is observed, even though they are having different physicochemical properties. It was found that this interaction was enthalpy driven, and the interaction of these drugs with the stationary phase were mainly hydrogen bonding, pi basic, pi acidic interactions, and dipole-dipole interactions between the carbonyl groups and the phenyl carbamide moiety of the stationary phase, with primary and secondary amino groups in the metformin and the aromatic ring systems of the gliflozins. Now, what is interesting to know here is the elution order which was obtained using this chromatographic technique was matching with, which agreed with the docking score of the drugs which were obtained through the computational tool. Similarly, it matched with the free energy parameters as well. And the greenness score, because we are using less of organic solvent, toxic, and more of carbon dioxide, the greenness score was 0.84. And one can understand through this greenness, this for agree matrix was used to calculate greenness of this method. And likewise, there is another example where 4 stereoisomers of luliconazole, an antifungal agent, were separated on an amylase based chiral pack 1H column. The Ventoff plots revealed that the chiral separation was essentially entropy driven. The results from molecular docking studies reveal hydrogen bonding and pi-pi interactions, and these are the major interactions which are occurring between the analytes and the stationary phase. The elution order and the binding energies which were calculated were in good agreement with the elution order. If you can see the elution order of those 4 isomers, they were in very good agreement, and a score of 0.88 was obtained using this method and using supercritical fluid chromatography. Now, in this, this is another example where enantiomer separation of 3 antihypertensive drugs, etenol, metoprolol, and propanol. These are very common drugs, and these are chiral drugs. And they were separated again using SFC, and all the previous studies were done with this as well. The main intention was to find out the greenness of these methods. Computational tools were applied to it, free energy was calculated, binding energy was calculated, and it was apparent from all these values, these results, that hydrogen bonding and the hydrophobic interactions were the dominant interactions. At the same time, all 6 analytes were resolved within a very short time, within 5 minutes. That means more number of analytes, as I said, lesser would be the energy consumption and better would be the greenness. And the greenness of this method was 0.87. And in this last case study, 15 co-formulated binary antihypertensive medications using a single elution protocol were separated using SFC. That means 15 analytes were tried they were separated using a single elution protocol, which was a combination of carbon dioxide and 0.1% formic acid and methanol. And eventually, the score that was calculated using agree matrix was 0.89. So in conclusion, what we can say that green analytical matrix, especially agree matrix, is a system for the assessment of greenness of analytical procedures, and certain salient features of this matrix includes that it is comprehensive, It includes all 12 principles of green chemistry. It is flexible. That means different volumes or different weights can be assigned, whether input weights or the waste generated, so that it gives a lot of flexibility. It is very easy to interpret through those pictograms. It is very easy to perform, execute with a very user-friendly software. And the entire exercise takes hardly 5 to 6 minutes. You just need to enter the information, the required information for each principle. And once we are done with all 12 principles, we get a final score as it was evident in the case studies. And one can have achieved the greenness score finally for our method. These were some of the suggested readings which I would recommend if one wants to read more about these green analytical procedures or metrics to calculate greenness of the method. And with this, I end my talk. Thank you for your patience. Thank you very much.